Okay, I ran out of time in the last video, so this video is going to be dedicated to strong and weak bases exclusively. So if you haven't watched the prior video on strong and weak acids, you need to watch that one first. Okay, so let's begin by comparing strong bases and weak bases. Okay, so the strong bases are the group 1 and group 2 hydroxides. And I'm talking about the groups on the periodic table. So that means the first column and the second column. So again, it's good if you just memorize these. We're talking about sodium hydroxide, potassium hydroxide, etc., etc. We're talking about magnesium hydroxide. It's going to be group 2. What's down there below that? Calcium hydroxide, and so on. Okay, so those are your strong bases. And remember, number one thing about what makes it strong is it goes to completion to the right. Okay, so in other words, if we put something like KOH, potassium hydroxide, in solution, we know that it is going to totally 100% dissociate into the potassium ion and the hydroxide ion. So it's going to be, for every 1 unit of this, you're going to get 1 unit of that. If it's 1 molar KOH, you're going to end up with a 1 molar hydroxide concentration. Okay? Very simple, very basic. Ha ha ha. Pun fully intended. On the other hand, the weak bases. So we can represent any general weak base with this letter B, like I've done there, okay? And we know if they're put in solution, again, according to Bronsted-Lowry, they are going to be a proton acceptor. So it's going to produce the conjugate acid, BH+. Again, I get a little bit lazier. I should put aqueous symbols on everything. It's going to produce that, and it's going to produce hydroxide. But of course, really, really important and critical to the whole thing is remembering that this exists in equilibrium, okay? So just like for weak acids, we expect only a small proportion of this to actually go over to the right. You know, something like 1% or less, and more like 99% of it staying here in its undissociated regular molecule B form, okay? It's, you know, you don't necessarily have to memorize any particular weak bases, although a really common one that you see a lot is ammonia, NH3, and any like derivative of ammonia. So something like, you know, I don't know what this would be, methylamine, something like that. Anything that's got NH2 in it, these are weak bases. NH3, NH2, and ammonia, or an amino group. These are going to be weak bases. Okay, so remember that, and this goes back to the Arrhenius definition of acid-base. Remember that the ion in focus for base is always hydroxide. Okay, we are obsessed with hydroxide when it comes to bases. For acids, we're obsessed with the proton or hydronium H3O+. Okay, and so this one's all about determine how much hydroxide. What's the concentration of hydroxides in solution? So let me show you an example and a comparison. All right, so let's compare 1 molar NaOH, and this is a group 1 hydroxide, so it's a strong base, to 1 molar NH3. This is a weak base, ammonia, okay? And what we mainly want to ask ourselves is how much hydroxide, what's the concentration of hydroxide in each one of these things? Pause the video and see if you can figure out what it would be for the NaOH. Yes, for the NaOH, it's quite simple. The hydroxide ion is going to be equal to the concentration of NaOH because it's a strong base. So that's going to be equal to 1 molar, right? We know that if you put NaOH in solution, it just straight up 1-to-1 produces the Na plus and the hydroxide. But this is not the case for the weak base ammonia. What do we have to do to figure it out? Well, we know that when we put ammonia in solution, I'll try and be a good boy and put all my proper symbols on here. We know that when we do that, it's going to act as a base, but very importantly, equilibrium, right? Equilibrium. So what's it going to do? It's going to accept the proton from water and become the conjugate acid ammonium ion, NH4 plus, and it's going to produce some hydroxide. But how much exactly is it going to produce? This is the question. Okay, well, just like we did for the weak acid example, we're going to have to use a rice table or ice table to figure this one out, and we're going to focus on the equilibrium line, because at the equilibrium line there will be an equilibrium constant. And just like for the acid, there's a special equilibrium constant for a base, and we call it Kb. Kb works just the same. It is the products, okay, in this case the ammonium ion concentration and the hydroxide ion concentration, divided by the reactant, NH3, and it would be water, but we don't include it. It's like a constant. We just don't include the concentration of water, and water, that makes our heads explode. Okay, so this is what we're after. We're going to create a rice table here for this example, and we're going to figure this out. Now, if you look up the Kb for NH3, it would have to be given to you, or you'd have to be able to find it. More on that later. You'd find out that it is 1.8 times 10 to the minus 5. That might have been the exact same as the Ka that we used for the weak acid in the last video. Pure coincidence. But this is what the Kb is for that. It is a small number. Okay. We fill out all the numbers. We know we had 1.0. We had nothing. We had nothing. We know we're going to lose some amount over here, and we're going to gain that exact amount over there. Again, everything's 1 to 1 to 1 to 1. So over here, we're going to have 1.0 minus x. We're going to have x. We're going to have x. Once again, I'm just going to switch colors to try and make this a little more obvious. We're going to forget about that minus x, because we're going to assume that because the Kb is so small, that x is really tiny relative to 1.0. So at the precision of this experiment or this example, it's not going to matter. Plus, it makes it easier for us mathematically. We don't have to solve a quadratic. So there you go. Gotta love the math of chemistry. So NH4 plus is x, hydroxide is x, so that's x squared on top, and on the bottom you got 1.0. So you go ahead and solve for x here. It's gonna be just the root of 1.8 times 10 to the minus 5. Punch that into your miraculator. And you get that the x is equal to 0.0042. Yeah, I guess I should answer with 2 sig figs, right? Okay, which is also the hydroxide concentration. So you can see, if you go back up and compare, that originally our hydroxide concentration for the strong base was 1.0, and our hydroxide concentration for the weak base is much, much less, 0.0042 molar. So that hopefully just gives you an idea of fundamentally what the difference is between a strong base and a weak base. And I'll put the workings back in view here so that if you want to pause it and look over, pause this video, look over this again. You can help make sense of that, make heads or tails of it.